Yesterday you all got yellow pieces of cardstock and you took notes on atoms and elements. Today we're going to talk about compounds, so please get those back out. Please take notes on them. Now we're going to be doing some of this rather fast because we want to have time to play the games. So I will put this onto the Moodle if you want to watch it later on your own at home. That way you don't have to worry quite so much about how fast we're taking notes, because I know some of you take notes slower than others. Yesterday, once again, we talked about elements. Today we're going to talk about compounds. Why do elements form compounds? Well, it is because of noble gas envy. All atoms want to be just like the noble gases. I put this picture up yesterday, and we talked about the different families having different number of outer shell electrons. The noble gas family has 8 outer shell electrons. It is full. As Matthew said, it is fappy, fat and happy. Okay, everybody else wants to be fappy. I refer to this as happy atoms. So everybody else wants to be a happy atom. And they do that by giving and taking electrons. Now, on the periodic table, they also have an ability to attract electrons. Okay, the further apart the atoms are from each other, the more strongly the negative will attract the positive. So, if they are far enough apart, and here we have electron dot diagrams for our 8 basic families, when they are far enough apart, they will attract differently. And we'll get ionic compounds. Alright, so let's stop and let's backtrack for a minute. Neon, 8 outer shell electrons. Fluorine has 7. What does fluorine want to do to get happy? Fluorine wants to add 1 more electron. If he does that, he'll be happy. Well, let's think about fluorine for a minute. He has 9 protons. And right here, he has 7 in his outer shell. He has 2 in his inner shell. So he has 9 electrons. 9 minus 9 equals 0. That's a neutral atom. But if fluorine wants to get happy and he adds that electron on, he now has 10 electrons, 8 in his outer shell, 2 in his inner shell. 9 minus 10 gives us a -1 charge. Okay? That's what fluorine does in order to get happy. Oxygen needs 2. Oxygen has 8 electrons. He has atomic number of 8, so he has 8 protons. He has 6 in his outer shell, 2 in his first shell, so he has 8 electrons. If he adds 2 to that, then he'll have 10 electrons and he'll have a -2 charge. Okay? And we've looked at that. Okay? I'm going to print some of these off for you so that you can copy them onto your yellow sheet if you want to, rather than taking the time to do that right now. But this is essentially what I had on the board yesterday, at least this part. The first family has 1 outer shell electron. He's going to give that electron away and have a +1 charge. The second family has 2 outer shell electrons, so on and so forth. Sodium, first family, giving away that electron. Chlorine, 7th family, taking that electron. Sodium ends up with a positive charge. Chlorine ends up with a negative charge. Now let's get some terms out here. These are what we call ionic bonds because they form ions. An ion is a charged particle. One point when I taught junior high, I allowed them all to change that definition in the back of the book to charged atom. But really, it becomes a particle. I was young. I didn't know any better. Ion is a charged particle. Positively charged ions are called cations. Okay? It's got a plus right in the middle of it. Negatively charged, that was bad, ions are called anions. Okay? Cations, positively charged, anions, negatively charged. And the anions pull hard enough on electrons that they can pull those cation electrons away. and keep them for their very own. Okay, that's what forms an ionic bond. If we look at an example, aluminum. If I draw his dot formula, he has 3 electrons. He wants to get rid of those 3 electrons. If he does, he'll have a +3 charge because aluminum has 13 protons. And if he gets rid of 3 electrons, he'll only have 10 electrons. 3 minus 10 would be a +3 charge. Chlorine, on the other hand, has 7 outer shell electrons. He needs to gain 1. And we put these together. Aluminum is going to give 1 chlorine. Oops, I didn't put the L in. 1 of his electrons to this chlorine, and he's going to say, bring 2 friends. So ultimately, aluminum is not going to be satisfied until he has 3 chlorines attached to it. Okay? This meets the law of zero charge. The law of zero charge says whatever the charges of the ions are, they have to add up to 0. So we need 3 negative 1s. 3 minus 3, 0. Magnesium has 2 outer shell electrons. He's going to be a +2 charge. Bromine is just like chlorine. He's got 7 outer shell electrons. He's going to be a -1. And we get magnesium bromide. Sodium is a +1 because he has 1 outer shell electron to give away. Oxygen has 6 outer shell electrons. He needs 2. We'll need 2 sodiums to satisfy the oxygen. Again, don't try to write all this down right now. Just listen to what's going on. It'll be on Moodle for those of you that want to look further. Phosphorus has 5 outer shell electrons. He needs 3 to be happy. Now, this one's a little trickier because if we want to follow our law of zero charge, we've got numbers that don't divide into each other. So we're going to look for the least common multiple. Least common multiple of 2 and 3 is 6. So if this is a +2 charge, and we'll need 3 of them to add up to 6. Oh, that needs to be a 3. And the phosphorus is a -3 charge, so we'll need 2 of those. So we end up with calcium phosphide. Carbon can do a +4 charge. He's got 4 outer shell electrons. Chlorine, and this is really misleading because carbon and chlorine actually do not form an ionic compound. This is an old chart that needs to be removed. All right. Ionic compounds. You can do that. Now, covalent compounds means they're sharing. These are going to be nonmetals bonding with nonmetals. And they share the electrons. The electrons are on there and they share. Here you can see an ionic bond, 1 electron's given away to the other. Here the 2 electrons are shared. Covalent bonds, they still want to get 8. But they're going to do it by sharing because neither one can pull hard enough to really rip those electrons off the other guy. Okay? When we name covalent compounds, we use the Greek prefixes. If there's 1, we use the prefix mono. 2 is di, 3 is tri, tetra, penta, hexa, hepta, octa, nona, and deca for 10. Okay? Always, always, always. Now, the one exception, and chemistry is full of exceptions, if the first element is mono, you may drop the mono. Let's practice some naming. Antimony is SB. It doesn't have a prefix on it, which tells us, it's also the first one that tells us it's a mono, so we only need a 1. Tribromide, bromine with 3. Hexa, that's a 6. I shouldn't put a +6 because that'll be misleading. So we need 6 borons. Silicide is silicon. That's a really bad example. It should be monosilicide. And we would have B6S. Chlorine dioxide, once again, since there's no mono, we can assume there's only one chlorine. Chlorine dioxide, ClO2. Hydrogen iodide. Hydrogen is going to, there's no mono, so there's only one hydrogen. Iodine, this should be called hydrogen monoiodide. I did not do a good job of picking these. I apologize. Next one, iodine pentafluoride. Pent is 5. Dinitrogen trioxide, N2O3. Ammonia is NH3, which is a whole different naming system. Again, I should have vetted this a little bit more closely. Phosphorus triiodide. All right, let's try it the other way. P4S5. Tetraphosphorus. I'm going to make this zoom in. Tetraphosphorus. Let me get a white background. Tetraphosphorus pentasulfide. Nitrogen dioxide. Selenium hexafluoride, disilicon hexabromide, sulfur tetrachloride, carbon tetrahydride, diboron monosilicide, and nitrogen trifluoride. All right, so you guys are going to play dominoes. You're going to get a sheet that looks like this. You're going to take, you're going to pass all the cards out. And let's say this is your first card, or your first domino that you put down. And my friend Mr. Downing, he looks at his, and he can actually play a card. So he's going to play let's see. What can he play? I don't even know. He's got carbon tetrachloride, so he can play. We need to find carbon tetrachloride, or we need to find the other one that's on there. So let me do this. I should go back and edit that out, but I'm not going to. I don't have time. So on our example, you can take the carbon tetrachloride, and you know how to play dominoes. We're just not going to have any doubles. That might be kind of fun to have doubles. So the carbon tetrachloride would butt up to each other. Now you're going to look for zinc chloride, and somebody who has zinc chloride will get to play it. Okay? So take your time, work in pairs to do this, and then the substitute's going to hand out a review sheet for you that you will use then to work on this weekend. We'll go over that on Monday, and hopefully we'll be ready for finals. Okay? Great.